Well, hello everybody, and thank you for taking time out of your schedule to listen to this Waters Science Spotlight. My name is Jonathan Turner, and I'll be presenting to you today on retaining and separating polar acidic compounds, understanding mixed mode reverse phase anion exchange chromatography. We'll start off with a quick overview about what mixed mode chromatography is. I'll then transition into our brand new Waters Atlantis Premier BEH C18 anion exchange column. I'll talk about one of the new features of this column, which is the MaxPeak high performance surface column hardware. I'll then migrate into tips and tricks for methods development and wrap it up with a very quick summary. If we first start off about looking at mixed mode chromatography, which is also referred as multimodal chromatography, it refers to chromatographic methods that utilize more than one form of interaction between the stationary phase and the analytes in order to achieve their separation. What's distinctive from mixed mode when we talk about conventional single mode or just reverse phase chromatography is that the secondary interactions in mixed mode cannot be too weak. They have to contribute to the retentions of the solutes. Below are just some examples of different mixed mode chromatography stationary phases. You might have things like Hillock ion exchange, Hillock reverse phase, ion exchange HIC, or maybe even SEC ion exchange. For today's seminar, I'm going to focus on ion exchange reverse phase, specifically reversed phase anion exchange. So mixed mode chromatography has been around for quite some time now. Specifically, mixed mode columns have been around for many years as they provide certain benefits to separation scientists. Some of the benefits are that mixed mode columns allow the retention and separation of both polar and nonpolar analytes in a single run. The selectivity on a mixed mode column can also be optimized by adjusting mobile phase, ionic strength, pH, or organic solvent. And the selectivity can be finely tuned for separation of compounds that vary widely with different physicochemical properties. Another benefit is that you don't need to use ion pairing reagents in the mobile phase for separating out highly hydrophilic or charged analytes. And this simplifies the mobile phase, and these mobile phases are typically compatible with mass spectrometry. One of the benefits where we see mixed mode columns come into play is specifically for the retention of polar acids under reverse phase conditions. Typically, retaining polar acids under classic reverse phase can be quite challenging to do with a traditional C18 column. And that's due to primarily the chemistry. Maximum coverage C18 chemistries will create a hydrophobic surface that's not ideal for retaining polar analytes. Secondarily, ionized surface silanols cause a negative surface charge, which will repel anions. Another issue is with the stainless steel column hardware itself. Targeted acidic analytes, things that have phosphate groups, carboxylates, or sulfates, can bind to the metal ions in the flow path. Now, there have been a bunch of workarounds that try to address these challenges with common reverse phase columns. You might use something like an ion pairing reagent, but they have drawbacks, long equilibration times, and the ion pairing reagent might not be compatible with mass spec. Derivatization might be a technique you might use, but this can often be time consuming and a potential source of variability. Ion exchange methods are often used for polar acids, but they're not ideal for a mixture of acids, bases, and neutrals, which often occur in a sample. Hillock is the preferred technique for polars, but Hillock as a technique has its own problems, things like long column equilibration times and finding a compatible sample solvent. To address the metal ions in the flow path, often chelating reagents are added to the mobile phase. And adding these types of additives to the mobile phase might make that mobile phase not mass spec friendly. So Water's solution was to create its own reverse phase anion exchange column, the Atlantis Premier BEH C18 AX column. It's a mixed mode reverse phase anion exchange stationary phase. It's based on a new highly retentive 95 angstrom ethylene bridged hybrid particle. The surface bonding is optimized for the retention of polar acids across a wide pH range. It has a proprietary reverse phase anion exchange bonding, which is highly reproducible and provides an alternative selectivity to traditional C18 bonded stationary phases. We've also implemented a new technology in the hardware, Max Peak High Performance Surfaces. This is designed to reduce losses due to analyte surface interactions that are often found again with certain acidic probes interacting with the metal in the flow path. So let's start off by taking a look at the chemistry of the Atlantis Premier BEHC18 anion exchange column. I'll talk a little bit about the base particle, and then I'll talk a little bit more about the bonded phase specifically and how that impacts the retention, water wettability, reproducibility, the stability at both high and low mobile phase pH conditions, and lastly, its selectivity. So when we decided to create this stationary phase, we decided to start off with a highly retentive BEH 95 angstrom particle. It's a hybrid particle that has equivalent retention to our high-strength silica particle technology. If we look at the comparison of the HSS T3, the BEH 95 with the T3 bonding, and the BEH 130 with the T3 bonding, we can see that the BEH 95 angstrom with the same bonding has equivalent retention to that of our HSS T3. And you can see how we've achieved that by increasing the surface area of the base particle on the BEH 95. Now, by reducing the pore diameter, we were concerned about the possibility of the stationary phase de-wetting. We knew that to retain polar compounds on a non-polar surface like a C18, typically the approach is to reduce the amount of organic in the mobile phase. Typically, scientists will make the mobile phase as weak as possible or 100% aqueous. But again, the risk is the potential problem of the stationary phase de-wetting. The non-polar surface expels the aqueous mobile phase. The chromatographic pores actually dry out. And again, this is called pore de-wetting. So what's the mechanism behind de-wetting? So let's take a look at the mechanism of retention loss caused by de-wetting. It's based on the theory of pore filling by non-wetted liquids using mercury pore symmetry. Pressure is applied to force the non-wetted liquid into the pores, and when the pressure is released, the liquid extrudes from the pores. We can assess or measure de-wetting in a column very simply. Typically what we do is we condition the column or equilibrate it with a mobile phase that contains 50% water, 50% acetonitrile. And then we change to 100% water and we measure the retention factor. We then stop the flow. And by stopping the flow, we decrease the pressure on the column. And if the pores are very hydrophobic, they can de-wet or actually push the mobile phase out of the pore. We then restart the flow in the 100% aqueous mobile phase conditions, and we once again measure the K prime. And we're able to compare this post K prime versus the initial K prime to get a percent change in retention or a percent de-wetting. So what does this look like chromatographically? So this is a retention loss after stopping and restarting the flow using 100% aqueous mobile phase conditions. If we look at the top chromatogram for the Atlantis Premier BEH C18AX column, we see the black trace is the initial fully wetted retention factor of this column. After we've stopped the flow and restarted it in 100% aqueous, that's the red dotted trace. We see roughly about a 4% decrease in retention. If we compare that to a maximum coverage C18 stationary phase or Acuity UPLC HSS C18, when we apply the same testing, you can see roughly a 50% decrease in retention. The Acuity UPLC HSS C18 column is not 100% water wettable or 100% water compatible. So we would say that this column, the Atlantis Premier BEH C18AX, is a good column for 100% aqueous mobile phases, where again, the Acuity UPLC HSS C18 column is not a good stationary phase for 100% aqueous mobile phases. When we look at the stationary phase in our bonding process, it's very similar to what we do with our current CSH particle technologies that we currently have on the market. We start with our unbonded 95 angstrom BEH particle. We then apply a controlled surface charge using our new charge modifier, which is an alkylamine. We then bond an end cap with our T3-like C18 bonding optimization for compatibility with 100% aqueous mobile phases. And this T3-like C18 bonding is a mid-coverage C18 approach and end capping. If we look at the batch-to-batch reproducibility of this process, it's very reproducible. If we look at 3 batches shown here, the overlay trace from our QC test are quite similar, if not identical. You see very little difference in selectivity between these 3 batches, which are prepared on 3 different base particles and 3 different bonding steps. If we look at the batch-to-batch reproducibility one step further, we look at the relative retention of the analytes due to resorcinol. Now, this reproducibility is comparable to our state-of-the-art C18 stationary phases. If we look at the relative standard deviation values for, in this case, 27 different batches that span across 3 different particle sizes, you can see that the percent RSDs for the relative retentions are all less than 3%. And again, this stationary phase is as reproducible as our most current modern straight C18 bonded stationary phases. To assess the base stability comparison, we run an accelerated base stability test at pH 12.3, and we measure the time it takes to reach a 50% retention factor loss for a neutral analyte. In this case, we use propylparaben. The longer the bar, the more stable. If we compare our Atlantis BEH C18AX stationary phase to our CSH C18 and our Waters HSS T3, you can see that the stability is much better than our HSS, which is predicted because that is just a silica-based particle and shouldn't have much high pH stability. When we compare it to our CSH C18, which is built on our BEH 130 angstrom particle, you can see that the stability is a little bit less, and that's due to the fact that the Atlantis Premier BEH C18 AX is built on the 95 angstrom base particle, which has more surface area. In looking at some competitive columns that are out on the market, those were not tested at high pH, and the reason being so is that most of the mixed mode columns out there are based on silica-based particles and cannot operate under the elevated pH conditions that I'm showing here. If we look at how we've characterized the acid stability comparison, again, we use an accelerated acid stability test, and that's run at pH 1.3. In this case, we look at the percent loss and retention factor for methylparaben across a given time, in this case, 24 hours. We use a 0.5% TFA solution, and we run this at 60 degrees C. The shorter the bar, in this case, the more stable the stationary phase. So in this instance, the Atlantis Premier BEH C18AX column is very compatible in acid stability to our HSS T3 stationary phase. When compared to some of the competitive silica-based stationary phases out there, it's fairly comparable to the brand P mixed mode reverse phase AX. But if you look at the competitive material, the brand A mixed mode reverse phase anion exchange, you can see that that stationary phase has lost well over 60% of its retention in this 24-hour period, indicating that this stationary phase is not as stable under low pH conditions as our Atlantis Premier BEH C18 AX stationary phase. Lastly, what we wanted to look at the selectivity comparison for a mixture of polar acids, base, and neutral mixtures. If we look at the Atlantis Premier BEH C18 AX column on the top, you can see that peak 5, which is the acidic peak adenosine 5 monophosphate, you have much more retention for the acidic probe on this stationary phase due to anion exchange. If we look at the bottom chromatogram, which is our HSS-T3 stationary phase, you can see that the acidic peak is not well retained, but there's excellent retention for the basic analyte peak 4 procanamide. The acuity UPLC CSH C18 stationary phase falls somewhere in the middle, as that has a slight positive surface charge on this chemistry. So now I want to take a look at the Atlantis Premier BEH C18 hardware. It's got max peak high performance surfaces. So what is max peak and what are the benefits to scientists? Well, max peak high performance surfaces are a new and innovative technology designed to increase analyte recovery, sensitivity, and reproducibility by minimizing analyte surface interactions that can lead to sample losses. Max peak high performance surfaces address problems commonly found with acidic analytes interacting with stainless steel column hardware. And this is the first column to use this max peak high performance surface technology. So there are benefits in this technology, again, especially to acidic compounds. If we look at guanosine 5-monophosphate here, on a stainless steel column, you can see that the intensity is low and it has a pretty high tail. If we compare that hardware to the max peak high performance surface hardware, we can see roughly a 30% increase in area and almost a 45% decrease in tailing factor. And this benefit is commonly found with these types of analytes that are phosphorylated. If we look at the monophosphate or adenosine monophosphate shown here, you can see that with max peak, we get roughly about 2 times higher the intensity and less tailing. But if we look at the triphosphate version of this molecule, adenosine triphosphate, you can see that with the max peak high performance surface hardware, we get almost a 20% higher signal intensity. Without the max peak high performance surface hardware, this analyte is almost adsorbed to the stainless steel surface, and you can barely see it in the baseline of this chromatogram. Another benefit of the max peak high performance surface hardware is that you get consistent results from the first injection. Reproducibility results from the first injection on. So in this study here, we took a look at the molecule fructose 1,6-bisphosphate, and we took 12 columns. 6 columns had max peak high performance surface hardware. 6 columns were regular old stainless steel column hardware. We looked at the area count from injection 1 to injection 10 across these 12 columns. What's to be noted is that for the stainless steel columns, injection 1, you get much lower area count than injection 2 and injection 3 and so on. In fact, it doesn't really even level out even at injection 10. With the max peak high performance surface column technology, you get expected area counts from injection 1 all the way out to injection 10. Also that to be noted is that for the 6 columns of each that we tested, the error bars or the variability from column to column is much higher in the stainless steel columns than with the max peak high performance surface column technology. In fact, the max peak high performance surface columns have a very equivalent and very reproducible results from injection 1 to injection 10. So now I want to transition into methods development, or how to use these columns to their fullest. Looking at things like the aqueous organic concentrations that you can put in your mobile phase, buffer concentrations, and probably most important, mobile phase pH. So with mixed mode columns, there are multiple levers that you can pull to manipulate the selectivity. If we first think about the aqueous and organic mobile phase considerations, or concentrations, they're similar to our classic reverse phase, where the higher percent aqueous equals more retention. The weaker you make the mobile phase, the more retained the analytes will be. Buffer concentration is one of the levers that can be really important and utilized for mixed mode. Higher concentrations of buffer provide less retention for negatively charged acids and more retention for positively charged bases. Conversely, at lower concentrations, you get more retention for negatively charged acids and less retention for positively charged bases. Mobile phase pH could be the most powerful tool you can use to manipulate selectivity with this stationary phase. It controls the ionization states of your analytes, which we know is a key parameter for selectivity of ionizable analytes. But pH also affects the charge on the stationary phase itself. If you remember, this stationary phase is stable from pH 2 to 10. The surface charge begins to gradually decrease above pH 6 for the stationary phase and approaches 0 around pH 7.5. The pKa of this column is roughly around 7.5. So if we look at some retention comparisons, again, for that panel of analytes I've been showing throughout this presentation, which contains some polar acids, bases, and neutrals. In this instance, we're just increasing the buffer concentration, going from 5 millimolar to 10 millimolar to 20 millimolar. And I've just highlighted two peaks of interest here, the basic analyte, procanamide, and the acidic analyte, adenosine 5-monophosphate. As we increase the buffer concentration to 5 millimolar to 10 millimolar and to 20 millimolar, you can see that the more buffer we have, the lower in retention we get for the acidic peak, or peak number 6. And conversely, we get more retention for the basic analyte, peak number 4. And again, this just highlights that you can utilize buffer concentration to manipulate selectivity. If we look at this stationary phase and its dependence on retention on mobile phase pH, we get a slightly different story here. So in this instance, we're using 20 millimolar ammonium formate for all three examples. But again, we're just manipulating the pH now. We're going from pH 3 to pH 5 to pH 7. I've highlighted three analytes here, two bases, nicotinamide and procanamide, and again, the acidic probe, adenosine 5-monophosphate. As you go from pH 3 to pH 5, you can see that the two basic analytes increase in retention, and the acidic analyte significantly increases its retention. But as we go from pH 5 to pH 7.2, you can see that peak 3 doesn't really increase retention that much, where procanamide has a significant increase in retention, and the acidic analyte actually has a reduction in retention. So what's going on here? If we continue to look at the dependence of retention on mobile phase pH, if we look at this graph, which shows the retention factor versus pH for those three analytes I talked about on the previous slide, the two basic analytes, procanamide and nicotinamide, and the acidic compound adenosine 5-monophosphate. If we start off looking at the acidic analyte, the adenosine 5-monophosphate, you can see that at low pH, it's not very well retained. But as we increase the pH, say from pH 2.5 to 5, as this analyte becomes more negatively charged, it becomes more retained on the stationary phase. As we get above pH 5, the stationary phase is starting to become weaker. Even though this analyte's becoming more negatively charged, the stationary phase is becoming more reversed phase-like, and as this analyte becomes more hydrophilic, it becomes less retained. If we look at the basic analyte procanamide, at low pH, it's fully ionized and actually repulsed due to the anion exchange stationary phase. As we increase the pH, this basic analyte is actually becoming less basic. It's becoming more neutral. And as we get above the pKa of the stationary phase, it's actually being pushed off the column less. And as this analyte becomes more neutral, it's actually becoming more retained, as it's becoming more hydrophobic. If we look at nicotinamide, a simple base that only has one pKa, at low pH, it's ionized and repulsed from the column due to the anion exchange repulsion of the stationary phase with this positively charged analyte. But as you get above its pKa, say to about 4, 4.5, this analyte is uncharged now, or hydrophobic, and the retention of this analyte is consistent due to the fact that it's only being retained by classic reverse phase mechanisms. And here's an example of utilizing this stationary phase in a real-world separation example. This is the analysis of organic acids under reverse phase conditions using a mass detector. So separation of organic acids can be typically challenging. Often they're using maybe ion exchange chromatography, and those runs can take somewhere in the orders of an hour to an hour and a half to separate out these types of analytes. Classic reverse phase can be used, but again, you have to often add maybe ion pairing reagents or something to the mobile phase to get adequate peak shape. But with this mixed mode reverse phase anion exchange stationary phase, we're able to retain and separate out 15 of these small polar organic acids with excellent peak shape and good resolution. So just in summary, mixed mode reverse phase anion exchange columns are a powerful tool to retain and separate polar acidic compounds. Mixed mode reverse phase anion exchange columns can widen your selectivity space, which can be advantageous for methods development. Perceived challenges with mixed mode reverse phase anion exchange columns are addressed with Water's new Atlantis Premier BEHC18AX column. It provides increased retention and pH stability with the new BEH95 angstrom particle. It has excellent batch-to-batch reproducibility and utilizes familiar reverse phase methods development approaches, things like percent organic, buffer concentration, and mobile phase pH. If you'd like to find out more information of this stationary phase, you can go to our website, which is www.waters.com/Atlantis. And if you'd like, you can download this infographic, which again just highlights some of the key attributes of this stationary phase. And with that, I'd like to thank you for your time and taking time out of your busy schedule to listen to me in this Science Spotlight. Have a great day.